Welcome to AP Statistics. Today's lesson is section 11.1, part 1, inference for the mean of a population. I want to emphasize that at any time if you get behind, because I'm going to move fairly quickly so as to save digital space here. If you get behind, please just raise your hand and have the sub stop the lesson. Okay, so here's the big idea. Today's lesson is brought to you by the letter T. We'll see why in just a second. Conditions for inference. As always, when we're working through problems like we're going to today, you need to make sure that your data is from an SRS and your data is either normally distributed or n is sufficiently large. And those are two things that we've been talking about for a while. It was on the quiz last week. It'll be on the test coming up on Friday. Keep that in mind. The problem with the Z statistic. Here's why everything that we've been doing for the last 4 weeks is ridiculous. The Z statistic assumes we know the population's standard deviation, and that is impossible. Why is that impossible? Well, it's impossible because we're always looking for the mean. We're searching for this piece of information right here. Well, we can't possibly know that this piece of information if we don't know this, because the standard deviation is calculated from the mean. In practice, and we're going back here to chapter 1, 2, when we want to estimate the population standard deviation, sigma, we use the sample standard deviation, S. And let me remind you about S. Here's how we get S. First, remember that's the sample. Standard deviation. And that is calculated by taking the square root of something very, very big. 1 over n minus 1 times the sum of all of the data points, starting with the first one and going all the way up to the last one. We'll call that the nth one. For each one of those data points, let's call them xi, we find their deviation from the mean, or in other words, how far away are they from the mean? That's subtraction. We square it. Okay, we divide by n minus 1, we take the square root. So there's the definition of S. In practice, we're never going to use this formula, but I bring it up because I want to talk about this feature right here, the n minus 1. We're going to call that the degrees of freedom. And here's why we use this word freedom to refer to this. If you had to pick a data set, a bunch of xi's, and you knew S, you knew the sample standard deviation, you could make n minus 1 choices. Because you could pick the first data point, and you could pick the second, and you could pick the third, and you could pick the fourth, and the fifth, and the sixth, and the seventh, and you could pick all of them up until the second to last one, which you could pick, but you couldn't pick the last value. It would be decided for you because you need to have all of the xi's such that they equal the standard deviation. So the idea is you're going to have n minus 1 degrees of freedom, and you'll see how that's going to pop up today. Okay. This is William S. Gossett. He is also brought to us by the letter T. Standard error. You're going to see this language in your book. SE means standard error, and that refers to taking S and dividing it by the square root of n. And the standard error is referred to as the standard error of x bar. It's in effect, it's the standard deviation of our x bar. We call it standard error because it's error. It's how much are you missing the actual mean by when you find an x bar. You'll see how that's used right now. Okay, so let's compare this new t statistic with the z statistic. Okay. When we want to calculate z, here's what we do. We take some statistic, we subtract from it the actual population mean, and then we divide by standard deviation over the square root of the number of samples. And that gives us a z that is approximately normal with mean 0 and standard deviation 1. The t statistic is almost exactly the same with one notable difference. You're still going to have some test statistic, your x bar. You're going to subtract from that the mean, and then divide that by not the population standard deviation, but s, the sample standard deviation, over the square root of n. And that is referred to as the t-stat with n minus 1 degrees of freedom. Okay, that degrees of freedom ends up being important. It affects the actual t value. Let's picture a t distribution. Start by drawing a normal curve. So that's our normal distribution. Let's assume it's a standard normal. Now, whenever you invite new bits of randomness, and this S is more randomness, it's more variation into your statistical study, what that's going to do is it's going to spread the graph out. The normal is notable for having these tails right here and right here that are very, very tiny, that close off very, very fast. The t distribution, in comparison, has very large tails. So let's do a t distribution with 2 degrees of freedom. That's what that symbol means. A t distribution is going to have this kind of fat tail, and as a result of the fat tail, it's not going to reach quite as high in the middle. Okay, so that's 2 degrees of freedom. Let's also picture if we had, say, 9 degrees of freedom. Having 9 degrees of freedom is better than having 2 degrees of freedom. It means that we have a larger sample size, and that means that our sample standard deviation should be closer to the actual population standard deviation. So we're still going to have a fat tail. It's just not going to be quite as fat. So with 9, it's going to look something like this. And in fact, as the degrees of freedom go to infinity, the t distribution is going to approach z. In other words, as t gets larger, or as the degrees of freedom here get larger and larger and larger and larger, our graph pushes towards that normal curve. In the back of your book, you need to get out Table C. Table C is your t-table. This would be a good point to stop the video. In fact, I'm going to stop the video, and you're going to go to part 2. Start part 2 once everyone has their book out.